Welcome to Chapter 1.2 of College Algebra, Math 1314. Again, this is Professor Bailey at Brookhaven Campus. If you read my introductory blog post, you know that I'm a hiker, and this is from a hike in the middle of France. I was doing what's called the Le Puy Route. Great food, great people. It was a great time. Anyway, let's move on. Today we're going to look at functions and graph in section 1. So we're going to look at what a correspondence is and whether a correspondence or a relation is a function or not. And this is when you put in values of x and how they relate to y in the overall equation. We're going to figure out how to find function values or outputs using a formula or a graph. We're going to look at graph functions. We're going to look at how to graph functions, which is the same as what we did in the last chapter by plotting points. And we're going to be able to just look at the picture of a graph and determine whether it is a function or not. We're actually going to know what a function is first, and then we're going to find the domain and range of a function, either from an equation or from a graph. And then in the problems, we're going to look at some applied problems. Okay. So a function, even by our language, we have bodily functions, we have business functions, etc. When you go to the gas pump, that pump has a function to figure out how many gallons of gas you're putting into the tank, how much it costs per gallon, and give you a total cost. Okay. So a function is just a correspondence between the first set called the domain, which are the inputs. So in the example of the gas pump, the input would be the number of gallons. And the second set called the range, and this is your output. In the case of the gas pump, the output would be how much you have to pay at the end for your total number of gallons of gas that you pumped. The function then would be some kind of cost function or a cost per gallon function that takes the input, the number of gallons, manipulates it mathematically, and outputs your cost for the gas pump. Okay? A function, an equation is only a function if the input corresponds to exactly one member of the output, or the input or domain creates only one output or range. And that makes sense, right? You don't want your gas pump to act like a lottery machine. Not a lottery machine. What is that thing called when you pull down the handle? Oh man, a slot machine. Sometimes you win, sometimes you lose. You pump 10 gallons today, and assuming the price doesn't change, but today you have to pay $40, and tomorrow you have to pay $400. A function, by definition, is consistent. So as long as the function doesn't change, every time you pump 10 gallons, you're going to pay the same price. Every time you pay 10 gallons, as long as the price hasn't changed, the function of price, you're going to pay the same total cost. It is important to note that not every correspondence or equation is a function. You can have an equation that is not a function that can have more than one output answer. Okay, and even we have some things, and I'll give you some examples in a minute from our own real life examples. So this is just a way of kind of indicating inputs and outputs. On the left, you see where the arrow starts, a -6. When you put in -6, it creates an output of 36. When you put in an input of 6, it also goes to 36. -3 goes to 9, 3 goes to 9, and 0 goes to 0, okay? Because every time we put in -6, because there's only one arrow out of it, out of the input, this is indeed a function. Because I get the same answer. I get a consistent answer every time I input -6. I always get the same answer. When I input 6, I also get 36. Okay, we can share the outputs, but there can only be one arrow coming out of the input for it to indeed be a function. So this is a function because each member of the domain corresponds to exactly one member of the range. Each member of the domain, the input, corresponds to exactly one member of the range, the output, okay? The definition allows more than one member of the domain or the outputs to correspond to a different member of the range, okay? The way I suggest that you remember this is same input, same output. If every time I put the same input in, I get the same output, that means only one arrow coming out, or SISO, it is a function. It is a function. And again, you want this to happen. Every time you pump 10 gallons of gas, you don't want the pump to be acting crazy. You want it to create the same total cost. Of course, assuming the prices haven't changed. Okay? Now, what do you think's happening here? Determine whether each of the following correspondence is a function. Okay? Well, it's kind of confusing because there's a hell of a lot of arrows to begin with. But notice if the arrows are going from left to right, so these are our inputs. What are they called again? Domain. Inputs are domain, okay? And outputs, where the arrow is pointing to, are our range, okay? George Herbert Walker Bush only has one name, so that's fine. He's a function. William Jefferson Clinton, wait, he's got two outputs. So sometimes when we put input in of Clinton, sometimes we get Breyer and sometimes we get Ginsburg, okay? So this is a big deal. So this is where we have an issue where this is not a function because there is more than one output for several of these inputs. By the way, this is, I guess these are Supreme Court justices and who appointed them, all right? So this is not a function because the same input creates different outputs. The same input creates different outputs, SIDO. Same input, different outputs. If you have multiple outputs for the same input, you do not have a function. This is not a function, okay? A relation is just simply any correspondence between the first set, the input called the domain, and the second set called the range or the output, such that each member of the domain corresponds to at least one member of the range, okay? So you just get some kind of output, all right? A function is a certain kind of relation, and then we've already talked about that if you have same input, same output every time, it's a function. Same input, different output, it's not. So notice here, now what we're looking at is ordered pairs. And when we're talking about domain and range, input values are X values. Domain are X values. Output values are Y values. Range are Y values, okay? So we have an input of 9 and an output of -5. We have an input of 9 and an output of 5. We have an input or domain of 2 and a range of 4, output of 4. If we draw this with arrows, it might be easier to see. Notice that when we input 9, sometimes we get -5, sometimes we get 5. So this is the same input with possible different outputs. So this is not a function. When we're identifying the domain, we're going to identify all of the input values, okay? So we have 9, 9, and 2. Notice we do not have to write the 9 multiple times because this one 9 is fine, okay? When we're going to document the range, it's all the output values, or in this case, the Y values. So we have -5, 5, and 4. We should put those in, you really should put those in numerical order, but I guess it doesn't matter here for this notes. So see if you can figure out if this is a function. Look at your inputs. Maybe you want to draw it. Input, output, input X, output Y, input X, output Y, input X, output Y. Go ahead and pause if you want to try it and see. But notice when we draw it, you can see that there's a single arrow from every input. So this is indeed a function. Same input, same output every time. Same input, same output. Okay? So this is indeed a function. The domain is negative 2, 5, 0, 4. All the x values. The domain is the inputs or the x values. The range are the outputs or the y values. Okay. I'm just going to walk through this one pretty quickly. This one throws people off because they all go to the same output. And so often students will think that this is not a function. But again, notice same input, same output. Now, what's a good example of this? If you have a cell phone with limited data, let's say you have 5 gigabytes of allowable data. Sorry about my clock there. If you have you have a cell phone plan with 5 gigabytes of data. If you use, and let's say it costs $30 plus an additional fee over 5 gigabytes, okay? If you use 2 gigabytes of data, that would be your input, 2. Your output would still be $30. If you use 4 gigabytes of data, your output would be still $30. But if you use 6 gigabytes of data, now you have a different output, okay? So this is an example, that's an example of one of these that would look like this, where multiple inputs create the same output. And usually that's when you have a range of inputs, a range of values that you can use up into, you know. Again, a cell phone's a good example of that. Electricity's like that too sometimes. You get charged more after you've used more, okay? This is a function. No input has more than one output. Same input, same output. Every time you put in negative 5, you get 3. The domain is negative 5, 0, 6, and the range is just one number or coordinate. Again, the inputs, domain, are values of x substituted into equation. The outputs are the members of the range, are the resulting values of y. And so we're going to use a new notation when we do indeed have a function, okay? This is the functional notation, f parenthesis x parenthesis, okay? And this is read as f of x, the value of f at x, etc. Typically, we just say f of x, okay? F of x is another name for y. So what it's saying here is, what is the value of y when the input is a specific value of x, okay? So if I document an equation that says a function is given by f of x equals 2x squared minus x plus 3, notice this is another way of saying y equals 2x squared minus x plus 3, okay? This is just a different notation for the y value. F of x is the y value, okay? So when I look at A is saying, what is the value of y, f of 0? F of 0 is the y value when x equals 0. So all I'm going to do is to substitute in the 0 in the equation for every appearance of x. Okay, so I have 2x squared, 2 squared, minus x, minus 0, plus 3. I do the math and I get 3. Okay, so I can say that f of 0 equals 3. Another way I can write this is, because it's an x and a y value, this is 0, comma 3, or an ordered pair. I'm going to do the same thing with f of negative 7. This is asking me for what y equals. When x is negative 7, I'm just going to plug in the negative 7 for every appearance of x. 2 times negative 7 squared minus negative 7, 2x squared minus x plus 3, and I get 108. Now it gets a little more complicated because I can substitute in a different variable and really a function of a variable. This is 5 times another variable a, or a constant value, but it's listed as a letter, okay? When you are substituting in letters for x, etc., always use parentheses, okay? So this is not 2 times 5a squared, it's 2 times parenthesis 5a parenthesis squared. You need to square both of these. It's not 5a squared, it will be 25a squared, 5 squared and a squared. So when you're substituting in other variables or other letters into these functional equations, make sure you use parentheses. I would have even suggested to use it there because it's just a good habit. So here again, I get 5 squared is 25, a squared is a squared, so it's 2 times 25a squared. Be careful here too. We have a natural tendency to want to go left to right, and so a lot of times students will multiply this out and they'll get 10a and then square that and get 100a squared. So take your time, use parentheses, and remember parentheses come first. Here's one that's a little bit more involved, and this is a great example. I suggest you pause this video and see if you can get the right answer. Again, use parentheses. So we're going to put 2 times parentheses a minus 4 squared minus parentheses a minus 4 plus 3. Now, this first one is a FOIL, or a polynomial squared, right? So we have to FOIL that out. I'm not going to go through those steps. You should know that. And there's some good tutorials in your My Math Lab. And then I'm going to distribute the 2. And then I'm going to combine like terms. Okay? All right. When we're graphing these functions, we do it the same way that we did in the chapter 1.1. We simply plot points, build a table, and complete the graph. Okay? So notice here this table, instead of saying x and y, it says x and f of x. So if x is negative 3, we plug it in here. Negative 3 squared is 9. 9 minus 5 is 4. We pick out a number of values. We figure out the y value. Get it in your head that f of x is just another name for y. F of x is just another name for y. Okay? And then this is the ordered pair. This is what we're going to plot. X, y, x, y. Okay? We put them on a graph. Connect the dots, so to speak, and we have our graph. You also have your calculator. Make sure you know how to use the y equals button in your calculator and how to graph. Again, go into My Math Lab under Tools for Success, and there's a great tutorial, graphing calculator tutorial there. Look for graphing and go through that. It'll give you a great example and some good experience doing that. Okay. This is the graph for x cubed minus x. I'm not going to walk through these. I'm not sure why it doesn't have the table there. And then here's a graph for the square root of x plus 4. Okay? I think I'm going to walk through this pretty quickly. Again, here we just want to find f of negative 3 for x squared minus 6. We're going to plug that value in. Oh, I'm sorry. This is very important because this is often difficult. It wants us to find the function f of negative 3 given a graph. Okay, we can't see the graph yet. But what we're going to do is we can see that the x value is negative 3. So we're going to go along the horizontal axis, the x-axis, until we get to x equals negative 3. Now remember, that's a vertical line. This vertical line all the way up and down is x equals negative 3. So what we're going to do is we're going to go to negative 3, and then we're going to see where the graph of the function crosses x equals negative 3. We're going to go up to that point, and then we're going to see what its y value is. Because remember, f of negative 3 is the value of y when x equals negative 3. So we go to negative 3, see where the graph crosses x equals negative 3, and then look for the corresponding y value. Here we want it, which is 3. So f of negative 3 equals 3. If we want to do the same thing for 1, f of 1, we go to x equals 1, see where the graph crosses x equals 1, and then look at what that y value is. In this case, it's negative 5. Okay? These can be a little bit confusing when you're looking at graphs. Remember, inside the parentheses is the x value. Go to that x value and then see where the graph crosses that x value. What people get confused is they're saying, wait, it doesn't cross because they're staying on the x-axis. But remember, this whole line up and down represents the value x equals negative 3. Right here is x equals negative 3. Right here is x equals negative 3, etc. So it is not possible a vertical line, which is an up and down line, if it touches the graph of the equation more than once, then the equation is not a function. A vertical line only touches a function one time. Now remember, this is an up-down. So let's look at this. So for example, notice if we have an up and down line in the example here on A, everywhere that we draw an up or down line, it only crosses the graph once. So A is a function because no matter where we put a vertical line on A, it's only touching the graph once. In B, we have a different situation. Notice here, we cross this vertical line, which is blue, crosses at 3 different points. Now think about that. This might be x equals -1. So you have 3 coordinates, -1, maybe 5, -1, -1, -1, -4. And if you saw those as points, or if we drew those as the inputs and the outputs, notice that -1 now has 3 different outputs, or 3 arrows leading out of it. Same input, different output. So B is not a function. C again fails the vertical test. It touches in 2 places. Here we might have 4, 3 and 4, -3 or something like that. Again, we could draw that, but the same X creates a different Y. This is not a function. A vertical line can only touch a graph in one place for a function. A vertical line that touches more than once is not a function. Okay? So we can see here in D that D is not a function. In E, that's a little more confusing, but it is indeed a function because a vertical line only touches one point everywhere. F is one that gets a little bit confusing. But remember that when you shade in a circle, shade in a dot on a graph, it includes this point. If you have an open circle, it means it does not include. So if I drew a vertical line down through this, while it would go through the open circle means that value is not included. So in this case, F is also a function. Okay? When a function F, whose inputs and outputs are real numbers, is given by a formula, the domain is understood to be the set of all inputs for which the expression is defined as a real number. Now what that means is if there's a value that makes your equation undefined, then that value is not part of the domain. The domain means that you have to have an input that creates a real output. So let's go back to, maybe this will help you understand this. If we go back with the idea of the gas pump as a function, an example of an input that would not be part of the domain is -10 gallons. You cannot pump -10 gallons. That would mean that you're trying to put 10 gallons back into the pump. It makes no sense. That's not a real situation. Numerically, we have to create a real number when we put in a real number, okay? And you can think about this, and we're going to look at it in a minute. Like when you look at equations, what's not allowed? What's not allowed? What will create, for example, we cannot divide by 0. That's not allowed in math, all right? When an input results in an expression that is not defined as a real number, it's not allowed, we say that the function value does not exist and that the number being substituted is not in the domain, okay? When we're looking for domains, it's usually easier to figure out by looking at the equation. What kind of equation is this? And we have a fraction. Are there any rules that say something is not allowed in a fraction? Well, of course. You cannot divide by 0, which means that the denominator cannot equal 0. So x can be anything but something that would make the denominator 0, okay? So for example, f of 1, yeah, that's in the domain because when we plug 1 in, we get a real number out. However, when we plug 3 in, the denominator becomes 0 and the equation is no longer defined. So 3 is not part of the domain because the output is undefined. Okay? 1 is part of the domain because when we put in 1, we get a real number out. When we put in a real number, we get a real number. Here, when we put in a real number 3, we get an undefined expression. Okay? Here, we have another, fraction. So x squared plus 2x minus 3 cannot be equal to 0, all right? So what we want to do is solve that quadratic equation. We're a little bit early because we're going to be doing quadratics in the next section, I believe. But if we factor this quadratic, x plus 3 and x minus 1 is the factors of x squared plus 2x minus 3. Then we know that either x plus 3 can equal to 0 or x minus 1 equals 0. This will be true because if I'm multiplying two things, and if either of them equals 0, then the product will equal 0. And so we get these two values which are not allowed. These two values which are not allowed. So x can be, the domain is anything but x equals negative 3 or x equals 1. Okay, this is set notation. This says that this squiggle says x, the line means such that, or is defined as x is not equal to negative 3 and x is not equal to 1. Okay, so x can be anything but those two numbers. And this again is an example of set notation. You might want to Google set notation and interval notation and do some review of that as well. Okay. Remember, when we're thinking about a graph, the domain is all the x values, and the range is all the y values. Input, output. Input, x. Output, y. Domain, x. Range, y. Okay? Now, when you're looking at equations, there's two types of equations that are going to have limited domains. The first one we already saw was fractions, where the denominator couldn't be 0. If I have even roots, square roots, fourth roots, sixth roots, etc., remember that we cannot take a square root or an even root of a negative number. So we can find where this is undefined by making the inside greater than or equal to 0. You can take the square root of 0, which is 0, but you cannot take the square root of negative 1. So you can solve this mathematically by putting whatever's inside the radical, which is called a radicand, and setting it greater than or equal to 0. Okay? If you graph it, you can also see it here. Okay? You can put this in your calculator, etc. Now remember, the domain are all the x values. So we're looking along the x-axis. It starts at negative 4, and then it keeps going. So our domain is negative 4 all the way to infinity. The arrow on the right end is infinity. Now, this is called interval notation. You use a square bracket when it includes that value, and since it starts at negative 4, we're going to include that. You use a parenthesis when it does not include it, like greater than or less than, versus greater than or equal to or less than or equal to. We also always use parentheses for infinity or negative infinity because those aren't real numbers. Okay? Now, typically students do okay with the domain, but they get confused with the range. Okay? Remember, the range is the y value. So we're looking at the values along the y-axis that the graph covers. The lowest point on this graph is at 4, negative 4 on the x value, which corresponds to the y value of 0. The upper value, we can see that this keeps growing and inclining, so it's going to be infinity as well. And so here we go from 0. So it's bracket 0, comma, infinity, parenthesis. Be careful, because sometimes when we're doing interval notations, you might have parentheses on both sides, and those do not represent an ordered pair. They represent from one x value to another x value for domain, or from one y value to another y value for range. Let's look at one that's a little more challenging as well. We first look along the x-axis, and we can see, since there's arrows that are continually expanding to the left and to the right, this is just going to keep getting wider and wider and wider and wider. So our domain goes from negative infinity to positive infinity, and remember, we always use parentheses. However, our range, which are y values, be careful here, we don't go at -3, we go to the lowest value of the graph, and notice that's at -4, and then it keeps going up. So again, we're going to have a range from -4 with a bracket, because it includes -4, all the way up to infinity, okay? So what we're doing is we're looking at the lowest point of the graph and going across to the y value. When we're doing the domain, we're looking to the farthest left and the farthest right. For the range, the lowest and highest point.